Okay, so it's my great privilege to invite Karthik for today's 4th March first talk. So I have been following Karthik for last, I think 6-7 years. I've heard about him even much earlier, and he has an amazing trajectory. I mean, he has been to France for his studies, then to Israel, then to finally he has settled in US, and he had joined Rutgers University. So the way I have known Karthik is from showing hardness of approximation in the parameterized setting. So this is how my academic interaction with Karthik started. I have followed his works over the last 5-6 years in hardness of approximation for parameterized inapproximability. And most of the results, he is one of the, like for most of the results which we know in parameterized inapproximability, he is definitely one of the author or a person who initiated some of these. So whatever we know more or less in parameterized inapproximability at this point of time, he is one of the person who has done all these things. So today is my privilege to invite him. And today he will not talk about parameterized inapproximability, but he will talk about inapproximability or approximability of and a very important areas of computer science, machine learning, artificial intelligence, data mining, which is called clustering. So Karthik will be giving a 2-hour talk on hardness of approximation for metric clustering, one today and one tomorrow. So with these words, let me invite Karthik to give his talk on hardness of approximation for metric clustering. Floor is for you, Karthik.
Thank you, Saket, for the elaborate introduction. But yeah, I'm also inspired by Saket, doing works in approximation, so side of things. But today I'm going to talk about hardness of approximation, which is about now clustering problems. And since this is the first part of the talk is supposed to be more introductory, I've kept things slightly simple, and people should feel comfortable to ask questions in between and so on. So let's see. So where does clustering come? Suppose you had things like some handwritten digits and you want to group them. So you know that there are 10 digits and you want to group them into 10 clusters. And so this is a task that we have. And such that one idea to do this is take any image and you can think of it in grayscale. So it's some 28 cross 28 pixel image with zeros and ones. And you want to cluster this. So one idea is just to think of it as a point in 28 cross 28 dimensional space. And then you want points that are close, ideally mapped to things such that the 2 digits are essentially the same. So we have some notion of clustering, which is very hand-wavy. But let's try to make it a bit more formal. So we have some points in high dimensional space, and you have some notion of things belonging to the same group. And clustering can then be thought of as the task of classifying the input data into groups such that things within the same group are somewhat similar in some notion. And this is very important problem. It arises in various areas. For instance, it arises in bioinformatics, where you want to cluster regions of the gene together because they have some internal structure that repeats. It comes in partitioning data because you have market segmentation. You want to group, you want to divide things based on different categories. Or it also comes in summarizing news because you want to sort of take many news articles and come up with one candidate article. So you want to cluster it and find a cluster center. It comes in data exploration. You want to recognize patterns, rules. So there's a lot of explications for these things. And then once we know that there are a lot of applications, let's try to mathematically model this problem. So to mathematically model it, let's say we have some metric space, gamma delta, and your input is some points in the metric space. And you're also given as part of the input, the integer k, which is the number of clusters that you would like. Now, what would be the output? My output would be a clustering, but let's try to formalize clustering. It would be a pair, C and sigma, where C is a subset of your metric space, such that there are k points that you have picked in your metric space, that's C. And sigma is a mapping of every point in your input to a point in C. So intuitively, one can think of it as you picked k centers and you mapped every point of the input to one of the k centers. And what would we want from this output? We want that the classification is good, whatever good means. So this is where the modeling comes in. So you want the classification to be good. And so this is broadly put a framework for clustering. And this is what is called as the continuous version in literature, because we also have a discrete version, which you will see throughout today's talk. And in the discrete version, you're on top of the input, you're also given an additional subset of the metric space, and you would want to pick your k centers from the input candidate centers. So you don't want to pick your k centers anywhere in the metric space, you want to pick them from S. So there's just small distinction between discrete and continuous versions. But now let's go back to the question of what is a good classification. So this is all about how do we model this thing. And there are many different objective functions one would want to minimize, like k-means, k-median, k-center, min-sum, correlation clustering. For the sake of now, I will define three of them. Let's start with k-center. In k-center, you want to pick k points, k centers, k candidates, k centers, such that when you map every input point to its closest center, the radius of the balls is minimized. So you would want that, you want to pick k points and associate every input point to the closest point that is there. And the smallest radius balls that we have around the k centers is the k center objective. It is, in other words, you pick k points and you grow radially. And you're asking, what is the smallest amount I have to grow in order to cover all the input points? We also have k-median. Notice that k-center is dictated by the worst point that is classified. And in k-median, it's more of an averaging thing. You pick k guys and you map every point to the closest center. And on average, you are asking what is the distance from the input point to the closest center. And we also have k-means, which is sum of distance square. So where you take k guys and you map every point to its closest center, and you're asking in distance, what is the sum of distance square of every point to its closest center. So this k-means makes more sense in the Euclidean sense, because then it's connected to various notions of, if you're given a cluster, then the barycenter is the optimal center of the cluster. So we have these various objectives. There is no real truth as which one is better. It really depends on the data. But given that they are nice mathematical formulation, we can study each one of them. And of course, there are certain notions of clustering that don't even fit this framework, because in facility location, we don't even have this center k given. And you're given a cost for opening every new cluster center. And then there are things like hierarchical clustering, where you would want a tree classification of every point. But let's not go into those things now. So given these mathematical modeling, we can formulate a computational question, which is, given as input a set of input points to classify, a set of candidate centers, and an integer k, we want to find a classification that minimizes the clustering objective, where the clustering objective can be k-means, k-median, k-center, doesn't matter. So let me try to make it a bit more clearer in terms of a decision problem. You want to distinguish, given as input x, s, and k, you want to distinguish between the following two cases. The yes case, where there is a classification whose cost is less than beta, and the no case, where any classification will have cost at least beta, greater than beta. So this is a classic decision problem. And as it turns out that it's NP hard, like, just like this is the bitter truth, like it's NP hard, fine. It's like, as they say in Hindi, Karela. And then you're like, okay, let's try to salvage the situation. I'm an excellent chef. I know approximation algorithms. I can define very probably efficient approximation schemes for these things. And yeah, then fine. I won't get the optimal solution, but I'll get something really, really good. But it turns out that regardless of how much you work hard, there is a boundary, there is a limit to how much you can salvage the situation. Maybe you can approximate it to some, say, 4-factor or 5-factor, but you can't really do much better. The bitterness stays. So this is like, in some sense, the message of the talk, that we want to identify the boundary to which you can salvage the situation. And when we say salvage the situation, I mean, we want to find a classification which is good, but efficiently as well in polynomial time. So for instance, can we find a 4-factor approximation for k-means in polynomial time? Because we know to solve it exactly is NP hard. So where do these boundaries lie is the question. Okay. And this area in general, from a hardness point of view, is called hardness of approximation. And it's motivated by the fact that there are many important problems that are not tractable, which here means not solvable in polynomial time, assuming P not equal to NP. And we need to cope with this somehow, because you can't just say, okay, it's hard. So one way to cope with it is to design algorithms whose cost is close to the optimum. And for some fundamental problems, one can actually show a reduction where if you had an algorithm that solves a problem approximately, then you can use such an algorithm in polynomial time to solve it exactly. And designing such reductions is this area called hardness of approximation. And we're going to look at hardness of approximation for clustering in this talk. So let's redefine our question in terms of hardness of approximation. We want to solve things approximately. So in the yes case, we have a classification whose cost is beta. And in the no case, we have that for all classifications, the cost is at least 1 plus delta times beta for some constant delta greater than 0. And now this is an easier problem because we have a gap. So the input instances have a lot more structure. So at what value of delta can we solve it in polynomial time? And for what values of delta is it still NP hard? So this is the kind of question we are looking at today. And of course, we'll be looking at it for objective functions such as k-center, k-median, k-means, min-sum, all these things. Okay. So let's start with k-center. So let me recall what k-center is. Here you are given, I'm going to define only the discrete version. We are given two input point sets, X and S. X is the set of points which we want to cluster, also called as clients. And S is the set of candidate centers from which we have to pick K people. So classification here is a tuple, C and sigma, where you pick K centers from S and you map essentially every point in X to its closest center in C. And what you want to minimize is the radius. Is the max, so you go over every point, every input point in X and look at the distance to its center, and the objective, k-center objective, is the maximum of these things, and that's the objective we want to minimize. And here I'm looking at it in the LP metric, but you can look at it in any metric space. Now, what do we know for this problem? It's NP hard, like as we said before. And there is a classic polynomial time 3 approximation algorithm for this, where you first pick an arbitrary point in your candidate center, and then you pick next the point in the candidate center, which is as far away as possible, and so on and so forth. You keep repeating, and the point is to just keep picking centers that are very well separated and far away, and this can be shown to be a good 3 approximation algorithm. It's a natural greedy algorithm. And then now the question is, okay, can we do better? Because this is too simple. Can we come up with some more complex thing? And it was shown that in a fairly simple reduction, which we are going to see, that it's NP hard to approximate it to anything better. So 2.99 approximation is NP hard, and 3 approximation is in polynomial time. And notice that this is for the general metrics. So there is no real metric structure apart from triangle inequality. And then we can ask, okay, but what about LP metrics? We have a lot of topology here. Can we do something better? And of course, the previous algorithm, which just used triangle inequality, still works. So you have a 3 approximation algorithm. But now maybe you can do better, right? Like as an algorithm designer, I have so much more geometry to play with. But it turns out that it is still hard to approximate it to anything better than 3. But in the Euclidean metric, you can do better, and you can get a 2.74 approximation. Okay. But it is NP hard to do much better than 2.65. So there is this gap in the Euclidean K-center problem that you can do better than 3, but you can't do really much better because there's a lower bound as well. An NP hardness result showing you can't do better than 2.65. Okay. So this is the state of the art. And I wanted to give at this point a proof idea of how these kinds of reductions look. And let me say this, that I'm going to show you the proof for the general metric now. And tomorrow we are going to be dealing with LP metrics specifically. So I'm going to show how the embedding into LP metrics works tomorrow. But for today, let's go back to this result we had for the general metric, and I will show that better than 3 is hard.
Karthik, can I ask a question?
Yeah, sure.
So don't we read this center problem in our textbook, and that is factor 2 approximation. So what?
Right. The factor 2 is
either
when it's a continuous case where you can pick the center wherever.
Okay.
And not from your input candidate set, or your X is equal to S.
I see. Fine.
So if your input points you're picking, then it's 2. Otherwise, you get a 3. Yes.
Okay. Thanks. Okay. Otherwise, I was like getting a bit confused. Thank you.
Yeah, I think the 2 version is always known. Just for me, for easier for the rest of the talk to use this version.
Sure. Thank you.
I think so. Can you just repeat the greedy algorithm as well? I missed that.
So the greedy algorithm.
Yeah.
Right. So you first pick an arbitrary center.
Okay.
And now the next you pick the center that is farthest away from it, that covers as many points as possible. So I think it's easier if you look at it as just if you don't have any candidate centers at all, and you want to sort of cover, you want a case center from your input points that are there. You first pick any input point that you have. And then the second point you pick is the farthest to this point. And then the third point you pick is the farthest to both the points, and so on.
I see. Okay. Thanks.
Okay. So now I want to show this NP hardness proof of 3, which is very cute and very quick. It starts with this problem called max coverage, also known as set cover, where you're given a universe and a collection of subsets of the universe and an integer k. And your goal is to cover the maximum fraction of the universe using k subsets in your collection, input collection. And there's a theorem. This is one of the classic NP hard results shown by Karth, that it is NP hard to distinguish the case when you can pick k subsets that cover the entire universe versus the case when you pick any k subsets, then you miss at least one element in the universe. So let me repeat this, that in the yes case, there are k subsets, you can pick them and it covers the entire universe. And in the no case, any k subsets one picks is going to miss at least one element. One element in the universe is not going to be covered for any k subsets. And this problem is, in distinguishing this, is known to be NP hard. And we're going to reduce from this to the case where if there were k subsets that covered the entire universe, then we're going to create an instance of clustering where there are going to be k points such that every input point is a distance exactly 1 to its closest center. And in the no case, any k centers we pick, there will be a point in the input which is at distance 3 to all the k centers. And hence this gives us this gap of 3. So if there was a 2.99 approximation algorithm, then it is going to solve this NP hard problem in polynomial time, which shows NP equals P. Okay. So the proof overview is just in this one slide. We're going to look at the bipartite graph between the sets and the universe. And we're going to put an edge from a universe element U to a set S if U is contained in S. Now, you can think of it as the natural graph metric or whichever way you want it. But if there is an edge, we put a distance 1. And if there is not an edge, we say that the two things are at distance 3. And this naturally fits the graph metric as well. And now your candidate centers are going to be the sets. And the points that you want to classify are going to be the one in green, the universe elements. In the yes case, you can pick k sets, which are k candidate centers, such that all of the universe is covered. Now, what does that mean? It means that for every universe element, there is one of these k sets, which is covering it, which means it's a distance exactly 1. So the k center cost is 1. Whereas in the no case, any k candidate centers I pick, they correspond to k sets. For every k sets, there is a universe element that is not covered. And so there is that universe element is going to be at distance 3 to each of those k sets. So the k center cost is 3. So if one can decide the case where the k center cost is 1 versus the k center cost is 3 in polynomial time, then you're solving this NP-hard problem of set cover, which was shown to be NP-hard. And hence such an algorithm cannot exist. Okay. So from this, we get that 3 approximation can be done in polynomial time, but better than 3 approximation is NP-hard. Okay, so this is just a warm-up to what I want to show next.
Karthik, this is Aditya. There is a question in the chat.
Sure. So why can't you do this for 2? I'm guessing. Let's see. So why doesn't this work for 2? I mean, when you want to prove a hardness of approximation result, you want to prove the largest possible number. Because this, instead of 3, I could also put 2 and it would still be NP-hard. So it says that it's NP-hard for any number up to 3. I guess that's the question, right? Or was it the question for the algorithmic side?
No, that's fine.
Yeah. Okay, so now let's look at k-means and k-median. So here again, let me first focus on the discrete setting, and then I'll go to the continuous. You're given an input set X, which you want to cluster, and you have a set of candidate centers S. And here again, a classification is going to be a pair. And in the k-means case, you want to, it shouldn't be max, it should be sum. You need to sum over all the points in X, and such that the distance to its center square is minimized. And in k-median case, you want to sum over all the points in X such that the distance to its closest center is minimized. And now what do we know about these problems? These are NP-hard even when k is 2. So this is a very spectacular thing that even when k is 2, it's NP-hard. Of course, this is in the continuous case, because in the discrete case, if k is 2, then you can just go over all pairs of points in your candidate center. But also, even when the dimension is 2, so you're in the Euclidean plane, it's still NP-hard. So this is a very strong NP-hardness result, that either if your number of clusters is small, it's still NP-hard. Or if your dimension is small, if you're on the plane, you can't still use any of the geometry, it's still NP-hard. And moreover, it fits in this thing called W2 hard in parameterized complexity, which intuitively says that even among the NP-hard problems, it's quite hard. So when we can't solve things exactly, we look at approximation algorithms. So what do we know? We know that there is a 9-factor polynomial time approximation algorithm for k-means. So if the optimum cost was beta, so there is some classification whose cost is beta, then we can find a 9 times beta classification in polynomial time. And for K median, it's 2.67. Although I must say that there is a paper in this talk, I think, which improves this, but I don't know the precise details, so I didn't include it. In stock 2022, there should be this should have been improved to 2.4 something. But this is in the general metric where you were given nothing apart from triangle inequality. So these are the approximation factors which you can do in polynomial time. But what about in the Euclidean metric? Can we do better than 9 for k-means? It turns out, yes, you can do better than 9. You can do something like 6.357, which is not like 1 plus epsilon, but it's definitely much better than what we can do. So in other words, we can use the Euclidean geometry to prove better things. And in fact, we can do something stronger now, that if the dimension is fixed, then we have a p-tas. So notice that when d equals to 2, it's NP hard, but there is a p-tas when the dimension is fixed. And on the other hand,
Karthik,
yeah,
all these results which you are mentioning is for the continuous version or for the discrete version?
good. The general metric is, and the versions that I mentioned there are for the discrete versions.
Okay. And this Euclidean metric?
Yeah, and the Euclidean metric is also the discrete, except when fixed k.
Okay, fine. Okay, thanks.
So if you fix the dimension or k, then you suddenly have p-tas. And so this is sort of very contrasting, that it's NP hard, but okay, if the dimension or k is fixed, then we are good. P-tas is good enough. P-tas means that you can approximate in polynomial time to 1 plus epsilon factor for any epsilon greater than 0. Good. So we know things from the approximation point of view, but let's look at it from the hardness point of view. For the general metric, we have that it is NP hard to approximate it to 3.91 factor for k means and 1.74 for k median. So let me just stick to k means. So we have approximation of 9 is possible in polynomial time, and 3.94 is NP hard. So there's still a huge gap between the two things. And maybe I should just say my belief. I believe 3.94 is actually the right answer, because you can do 3.95 in FPT time. So there is no real reason to believe the hardness should be higher in NP. But if you ask for specific metrics, L2 and L1, this is where, I mean, so the theme of this conference is supposed to be recent trends. So I'm going to mention what was not known recently. So from like 2000, what we knew is that there is no p-tas in L2 and L1 metric. And around 2003, this was extended to L infinity. So the state of art understanding before, say, 2019 was that, yeah, we know that there is some slight improvement you can do in L2 metric. You can get a 6.3 approximation, but we are only ruling out p-tas. So we have some hardness of approximation for 1.01 factor. So there is the gap is much bigger when we want to look at LP metrics. And for the continuous version, it took some effort actually to even show that ruling out 1.0013 is NP hard. And this is even much more recent. So Vincent and Yu Wong and I sort of looked into this, and we were like, we tried to address this problem over the last 3 years, and we made some reasonable progress, because now we can improve things much stronger. So what we have to say is that in the L1 metric is as hard as a general metric. So approximating it to a factor of 3.94 is NP hard in general metric. And we said that's not just the general metric, it's true even for L1 and L infinity and so on. So these are very strong results. Of course, they're not completely NP hard results because they rely on conjectures, which I'm going to state next. But already assuming the unique games conjecture, we get the results in green, which are 1.17, which is a much better improvement than what was known. For L1 metric, we can prove 1.56 NP hardness and so on. But for the L infinity metrics, which is curious, we can actually get tight NP hardness, that NP, an infinity metric in log n dimensions, is as hard as the general metric. Okay, so let me just put all these results together. So what we have right now. So there is this conjecture that we put forth called the Johnson coverage hypothesis. And assuming that conjecture, for you show that in L1 and L infinity, we gain nothing by the geometry of the metrics, and it's as hard as the general metric. And we get some very improved L2 metric inapproximabilities as well. And for in L infinity, we can actually prove NP hardness results. And the continuous version as well, we get some improved results. And more interesting is that there is this new interesting framework to study things in. And this might potentially, at least at a philosophical level, set the platform which for proving things for traveling salesman, Steiner tree, and all these things, which I'm going to discuss tomorrow more on how this framework sort of extends to other things. So again, let's try to do some warm up. But now we are going to rely on a hardness of approximation result for max coverage. So I'm going to show this result, which is for general metrics. It's that given as input points at x, s, and k, in the yes case, there is a classification whose sum of distance square is at most the number of points you have. And in the no case, any classification, the sum of distance square of the classification is at least 1 plus 8 over e minus epsilon. Now, the expression 1 plus 8 over e turns out to be something like 3.94. Now, the reduction is going to be from the max coverage problem. And here, the input is just, again, a universe and the collection of subsets. And the output is to cover, using k subsets, as much fraction of the universe as possible. And there is a very, very non-trivial result by Uriel Feige, who showed that it's NP hard to distinguish the case when you can pick k subsets that cover the entire universe versus the case where any k subsets you pick covers at most 1 minus 1 over e fraction of the universe. And this result is tight because there is a simple greedy algorithm where at each point you pick the subset which covers the maximum fraction of universe elements that are not covered. And such a greedy algorithm already gives you an approximation of 1 minus 1 over e. And what this result says is that you can't do better than this very naive greedy algorithm that is there. And let me say that this result relies on the PCP theorem and so on, which were not there before. Like the previous result, you just needed classic NP hardness and you got the gap for free because it's a max objective. And whenever there's a sum objective, we need to rely on much heavier machinery. Okay, so the goal is to then start with this theorem and reduce it to this theorem on clustering. So, and the reduction is exactly like what we saw for K-center. So we're going to take sets and they're going to become candidate center. We're going to take our universe elements and they're going to be the points that we want to cluster called clients. So again, every set is a candidate center. Every universe element is a client that we want to classify. And we put a distance 1 if the membership holds that the universe element is in the set. And otherwise, we put distance 3. Now, let's look at the yes case. In the yes case, there are k sets such that every universe element is covered. So for every universe element, the distance is 1. And we have n universe elements. So the k means cost is exactly n. And in the no case, any k sets we pick are going to cover 1 minus 1 over e fraction of the universe. So for 1 minus 1 over e, we're going to pay distance 1. And for the remaining 1 over e, we're going to pay distance 3. And since k means is measuring distance square, that's going to give you 9. So it's 1 minus 1 over e times 1 plus 1 over e times 9, which sums up to 1 plus 8 over e. And so we get that approximating it to 1 plus 8 over e factor is NP hard. Okay. Now, I've been saying this thing called Johnson coverage hypothesis. Let me try to first say what it is, and then I'm going to state the hypothesis. I'm not going to show how any of the proofs work today. I'm going to defer it to tomorrow. And then I'm going to say some other additional results. So that's the outline for the remaining of the talk. So Johnson coverage hypothesis is you have this set system that you got from Feige, but it has this additional property that it still remains to be NP hard between 1 and 1 minus 1 over E. But even when this bipartite graph is a subgraph of the Johnson graph. Now, the Johnson graph is a bipartite graph where every vertex corresponds to a set, and you have an edge between two vertices if one set is included in the other set. So I'm going to make this a bit more formal. But the point being is that we need a strengthening of the NP hardness of Feige, that it's not just NP hard, but it's NP hard for instances which have some very nice structure. And then we can get these tight results for clustering. So that's the sort of message. Okay, so what is this Johnson coverage problem? Let's try to look at this. So your input is a collection of sets of cardinality T. So your input is E, which is a collection of sets of cardinality T over a universe of size n. And on top of this, you also have as input an integer k. And in the yes case, you can pick k many subsets of cardinality T minus 1, such that for every set of cardinality T, there exists one of the k sets of cardinality T minus 1, which is contained in it. And in the no case, any k sets of cardinality T minus 1 that we pick, the probability that one of the input sets of cardinality T contains one of the k sets is at most alpha. So this is the alpha T Johnson coverage problem, the two parameters here being the cardinality of the sets and the alpha, which is the soundness probability that we have. So let me repeat this again. So in the yes case, so you're given as input some subsets of cardinality T, and your output is you want to pick k guys or k sets of cardinality T minus 1, such that in the yes case, for every set of cardinality T, there is one of these k guys in your cardinality T minus 1, which is completely contained in it. But in the no case, given these sets of cardinality T, any k sets of cardinality T minus 1 that we pick, there is this 1 minus alpha fraction of the input T sets whose subsets of cardinality T minus 1 are not in this k sets that we picked. Okay, so this is this Johnson coverage set cover version.
Can you explain the soundness once again?
Right. So in the soundness case, so we have as input these sets of cardinality T, and we are going to pick k sets of cardinality T minus 1.
Correct.
And now each one of these sets of cardinality T minus 1 is going to cover some fraction of the sets of cardinality T. And the amount of the fraction that is left behind, which is not covered by any of these T minus 1 things, is going to be at least 1 minus alpha.
So Karthik, so like what your soundness is saying that for every this, the property is that so you're choosing T, so your over E can still get confused with your soundness. I'm sorry.
Okay, no, that's fine. Let's try to let me try to set precise things here. T equals to 2.
Okay.
Okay, if T equals to 2, then you can think of it as a graph.
Correct.
And now you're given a collection of edges. And in the completeness case, you have k vertices, which cover all the edges.
Correct.
And in the soundness case, given you pick any k vertices, it covers at most alpha fraction of the edges.
Okay, get it.
And now we are just generalizing it for higher things.
Fine, got it. Thanks.
Okay, and the conjecture is that as you increase t, the soundness, the alpha goes up to 1 minus 1 over e. So this is the conjecture that for every epsilon greater than 0, you can find some high enough t such that you can set that alpha to be 1 minus 1 over e, and it still remains NP hard. Okay, so let me make a couple of remarks now. That for t equals to 2, this is the vertex coverage problem. This is the maximization version of the vertex cover problem. And for this, we know that there is a 0.9292 polynomial time approximation algorithm, and that is tight, assuming the unique games conjecture.
So the previous one is max coverage on some special graph.
Right. So this is, again, set cover itself is a generalization of vertex cover.
Okay.
And max coverage is a generalization of vertex coverage.
And this one is a special graph.
Right. Right. It's a generalization of vertex coverage, but it's a specialized version of max coverage. So it's in between.
Okay.
And the claim is that the inapproximability behaves closer to max coverage than vertex coverage.
Okay.
That for t equals to 2, 0.9292 gap is tight. And we were able to actually show that if you go push t to 3, then the inapproximability does improve. So from 0.9292, it becomes 0.875. So it's going up and up and up. And the claim is it goes up all the way till 1 minus 1 over e, which is like 0.63 or 0.64.
So, Karthik, so from the positive perspective, is it possible to achieve this 7 by 8? Because I know for t equal to 2, there's a paper which achieves this 9292, I think.
Right.
But for 3 and 4, can we achieve this approximation factor?
Right now, I think yes.
Okay.
But I wouldn't be extremely certain of it.
Okay, fair.
But I think yes.
Okay, thanks.
And so once we have this, then in tomorrow's talk, we will see how this hypothesis gives you all these tight results for clustering. But let me just say the ingredients that are there for tomorrow's talk. So we're going to have these hard instances with all this structure from the Johnson coverage hypothesis. And then we will need tools, which are dimensionality reduction tools, because we'll have to control the dimension blowups and so on. And these dimensionality reduction tools, generally, we don't have dimensionality reduction tools for all LP metrics. This is not there. But for these instances, we have it for all LP metrics. And they come from some communication complexity transcripts. And apart from this, we need embeddings from these two dimensionality reduction tools are going to be combined with the embeddings of the general metric into graph metrics, and then the graph metrics into LP metrics, but for these specialized graphs. So these are the three tools that sort of come together to give all the tight results that we like. So I don't want to say more than this because I'm going to tell tomorrow more details. But let me just quickly state the results that we have. That for L1 metric, we get this 3.94 and 1.73, assuming the Johnson coverage hypothesis. And in fact, the weaker version for vertex coverage holds under UGC. So that's why we get the smaller, weaker versions, 1.56 and 1.14. And for L2, it's slightly weaker, which is as expected because we can do things usually in L2 metric. And for L infinity, we can actually show NP hardness. Okay, let me move to a different version now. Now, I want to move to the continuous version in L infinity in high dimensions, or in general metric, as one can think of it. And we have this very surprising result, because notice that for the discrete version, we were able to show 3.94 hardness, and I claim that that is tight. Now, let us think of a continuous version. Let's think of it as an algorithm designer. I'm not constrained by the fact that I have to pick centers from the input. I'm not given an input set of candidate centers. I can pick centers wherever I want. So as an algorithm designer, intuitively it feels like I have more freedom. But we show this very surprising result that the continuous version is actually harder than the discrete. That this freedom actually makes it harder to choose things, which is that for, let's say, in the k-means continuous version, we were able to show that approximating it to a factor slightly better than 4 is NP-hard. So you're given as input some n points in O of n dimensional space, and you want to sort of find a classification where you can pick centers wherever we want. And still approximating it to a factor better than 4 is, we show it to be NP-hard. Okay, so this is surprising because it shows to be harder than the discrete version. And notice that for the discrete version, we have an FPT algorithm which solves it to a factor 3.94. And for k-median, instead of 4, we get 2 because it's not distance square, but distance, sum of distances. And so the really surprising thing is that continuous is harder than discrete. And we can extend it to get some sort of constant by criteria inapproximability results and so on and so forth. And the more surprising thing is that assuming the unique games conjecture, this hardness results holds even when k is 2. So you just have to find 2 clusters, and you can't do better than 4 approximation. So this is a very surprising result. And we can show that the dependency on D, K, and L infinity is tight, because if you go from L infinity to say L2, this no longer holds. There are algorithms, when the dimension has to be n, it can't be log n or something, and so on and so forth. So we show various tight results that all of these are tight. So this is for the continuous k-means and k-median. In the last few minutes that I have, let me try to say a bit about min-sum. So min-sum is this very curious thing where you don't have a notion of candidate centers. It's just about partitioning data. So you're given as input x, and you're given an integer k. And what you really want to do is just partition the data into k, in x into k parts, such that the following objective is minimized, which is you look at each cluster and you look at all pairwise distances. So obviously, if a cluster is compact, the pairwise distances are all small within, all pairwise distances are small, and you want to minimize the sum over all clusters. It's a very intuitive notion, and it captures this notion of compact clustering. And there is a log n approximation. So this has been studied as well. It's one of the classic versions to be studied from the 70s. And there's a log n approximation to this problem. But the best we knew till 2003 was that ruling out a p-task, basically 1 plus epsilon.
So can you please repeat the objective?
Sure. Here there are no candidate centers. You're given as input a set of points x, and the goal is to partition x into k parts, x1 to xk, such that the following objective is minimized. So you go over each cluster, each x1 to xk, and for each xi, you look at all pairs of points in xi, and you look at the distance between all pairs of points and you sum it up. So it's the average distance of 2 random points within xi. And you want this to be minimized. Okay, so okay. It's a sum of pairs. A very natural notion to have, but we don't have even good approximation algorithms for this. It's O of log n, and the hardness is also very far away. So this is like really huge gap. And what we showed was that it's NP-hard, so we improved the inapproximability from. In the S case, you can sort of partition it such that the cost is at most n prime. And in the no case, the cost is 1.41 times n prime, where this 1.41 comes from some tedious calculations. And one of the key ingredients is that we showed this very curious thing. So recall the max coverage instances we had between sets and universe. We can't say anything about the girth of this bipartite graph. We showed that even when the girth is like log n over log n, this remains NP hard. And the way we did it was we took an arbitrary hard set system coming from Feige, and we found a way to amplify the girth, keeping the hardness of approximation constant as it is. And once we had a larger girth, then we could reduce it to this problem of min sum. Again, I want to avoid telling any of the proofs today because I want to reserve the proofs for tomorrow. So that's this. So today is going to be a slightly shorter version of the talk, and tomorrow is going to be longer. So what we had was improved inapproximability of k-means and k-median in the LP metric using JCH framework. Again, the emphasis here was that we knew it for general metrics from the 90s, and somehow we pushed in the direction of proving these results for LP metric. And also this very surprising result that the continuous version is harder in the general metric. And we also studied like the k-mean sum thing. I just stated a few results. So tomorrow is going to be more proof driven with a lot of these proof ideas and so on. But today, I just wanted to give a flavor of the kind of results and the motivation and the directions that have been taking place in the last few years with respect to hardness of approximation and clustering. So any questions? We have a lot of time.
Yes, please. Please unmute yourself and ask question, or you can also just write in the chat, and I will do that for you.
Hi, so I have a question.
Yeah,
so
please.
In one of the slides before, you showed a table for hardness using some conditional results, I guess. For
Right.
So what is what's the state of the art for the unconditional case?
Right. So you see here the UGC numbers. So the L infinity, these are NP hardness results. And we were able to show basically we can get just slightly below the UGC numbers for NP hardness as well. So something like 1.45 instead of 1.56, 1.13 instead of 1.14, so on and so forth, under just standard NP not equal to P.
Okay, thanks.
Anybody else?
Yeah, I have a question that while explaining the Johnson coverage hypothesis, it wasn't clear to me that was it for the vertex coverage or the maximum coverage problems?
Right. So vertex coverage is a special case of the Johnson coverage hypothesis. It's when T equals to 2. And in general, we are looking at when T is much larger. So when T is much larger, this becomes a special case of the max coverage problem. So in particular, if E was anything, right, and your sets were all picked at layer 1, that just becomes the general max coverage problem.
Okay, so it lies somewhat between the vertex coverage and maximum K coverage, I can
Right.
say so. Okay,
Right.
Thank you.
I have a question. In the min sum problem, what if you replace the sum by max? That also seems like a natural.
Yeah, I think for this, there should be easier things to prove. Because, yeah, for this, the original reduction of K center should more or less work to give you some number, some constant, which is there. Because there you have a bound that every cluster, like there are hardness results known where every set is containing exactly 3 elements and so on and so forth. And so in the yes case, you will have the tight clusters with size 3. And in the no case, there will always be one guy who's not covered. So it will give you some 1.5 or 2 or 3 inapproximability. You don't need a hardness a PCP theorem or any of those things if the original sum is replaced by max.
So you could replace any of the sums by max, is it? Because there are two.
Right. So the I in 1 to k, that sum I was referring for the k center reduction. If you replace the other sum by max, one can study it, but I don't think it's at least popular. But then you will need more non-trivial tools. Because then you're essentially talking of diameter of a cluster and you're summing over things. So this version, one should be able to show something, but I don't think it's explicitly studied, at least very popularly.
Any other question?
Hi. So I think you mentioned that I don't recall which case it was, but I think for the k center case, you mentioned that you have a hardness of 3.94 and using FPT time, you have an approximation of 3.95. Which
This is for k-means, right?
Oh, so you said that you believe that 3.94 is the tight case of hardness, I think.
Right.
So can you put forth some more intuition here why you believe FPT approximation would imply a polytime approximation as well?
Right. So the intuition is my ignorance to any NP-hard problem, which can be approximated in polynomial time to a factor c, and NP-hard to do better, but you can do better in FPT time. So there is no such, say for instance, for vertex coverage problem, we know that, so it either just collapses all the way down to FPT, solving it exactly. There is no reason for it to just lie in between. Say one wouldn't believe that 1.49 approximation to any problem is W1 hard, whereas 1.5 is in FPT, but the truth in the NP world lies completely different. Usually things align or either just collapse completely to FPT.
I can give you one counterexample, Karthik, to that.
Yeah.
Look at directed odd cycle transversal. Okay.
Right.
So it's just like its hardness of inapproximability in poly world. It's same as for directed feedback vertex set. Okay, which is we know that you cannot have any constant factor approximation.
Mm-hmm.
Okay. Now directed odd cycle transversal is W1 hard.
Right, and it has two approximation, I guess.
It has
right?
a two approximation, and
Right.
like so, it might have 1 plus epsilon approximation, that I don't know, but like it does have a factor 2 approximation.
Right. So then the question is, will it collapse all the way down?
Correct. We know that it cannot collapse to FPT, so it might
Right.
just collapse to 1 plus epsilon. So yeah, that's all.
Yeah. So just that one develops some notion of beauty of how things lie.
Correct.
And it just looks very weird if things are out of place.
I agree. Okay.
So yeah, that's why I said I believe. I don't want to. Beliefs are more aesthetic.
Agreed. Any other question from anyone? If not, then let me thank Karthik for this wonderful talk, and we hope to see more technical proof. And I hope all of you have got flavor of clustering and the kind of things and results people have been doing in this area. And tomorrow we will see the most latest developments to show some of this hardness, which Karthik will tell us. So thank you, Karthik, for such a wonderful talk, as always. So let me clap from everybody, and thank you. So yeah, so we'll see you again tomorrow at the same time for your talk.
Yeah.
Thanks a lot, Karthik.
Thank you.